Hello, ladies and gents. My hair is crazy. Let's fix that real quick. Alright, so, now that that's fixed, yes, I'm kind of using the camera like a vanity mirror. Something I probably should do before I start the stream, but whatever. Don't care. So, today is a red letter day. Specifically in that I've decided that the current terrain engine I'm using is garbage. It's not garbage, it's a difficult algorithm to find. It's a difficult algorithm to make use of. And when you're done using it, it's a difficult algorithm to heavily control. Because all of its data is generated from not just a tier 1 data set, but what I call a tier 2 data set, where it's data of data that's getting generated. And that creates a problem. Because if it's a tier 2 data set, it's more difficult to jump in, make modifications to the terrain, and then step away from it again, right? You kind of expect the terrain to get generated, and then you expect to be able to make some like user modifications on it. Specifically, the thing I've been fighting with is making it fit within a square and carving out a piece of terrain that is large enough for a player establishment to start on. And that's kind of problematic, because first off, the terrain system I'm using, even though it uses simplex noise, which is a gradient-based, or it's kind of a gradiated noise function, it still has problems generating a kind of terrain that I'm finding useful. And I'll just kind of show off what I mean here. I actually wonder, I don't think I have my terrain revealed. Let's quickly set perspective. Somewhere in here. Here it is. Specifically, okay. I actually don't care about the villager controller. I want the terrain version. Set node perspective masks. Okay, so let's jump in here, set node perspective masks, and just set this to 0, just so you can see all the terrain at once, and I can kind of get the point across a bit easier. There we go. So, why is this still hiding everything? The terrain controller should be the only one who's setting this. Oh well, at the end of this, we can also just call, not just reveal, but also add viewer. Reveal, add viewer. Just so we can see all the terrain at once and get an idea of what's broken here, and why I would ever want to rewrite this whole thing. Okay, so if you look at the center of the terrain, right, this looks pretty good. In fact, this looks fantastic. I love this. It's a set of uneven terrain that shows off its changes in height very cleanly. It's not a lot of wireframe data, right? If you look at this, that's a low polygon count for all the data that's being represented, and you have some areas that are a little bit dense, but that's fine. That's not the end of the world. Also, what is this? Notice this line here? That's bizarre and new. I've never seen that before. Huh. Anyway, so the terrain itself doesn't have a ton of data, right? This is good. It's nice and clean. We can pass it to the GPU in a pretty easy pass. The problem is it generates this. And this is not good, because you'll see like this chunk of terrain here, that's a lot of stuff that's outside of the region. The region actually ends way the heck back up here. This is where the random points stop getting generated. And the problem is, the moment you exit that region, we have these giant flat land masses that don't do us any good. And so that's problematic. That's really problematic. And I've been fighting and fighting for days, trying to get this into a kind of algorithm that's a little more controllable, called Fortune's algorithm. Somebody figured out a faster, easier way to do this, but the problem is most implementations you find are either academic, I should turn off the wireframe, they're either academic or they're so poorly written that it's very difficult to follow the flow. And while I read all the white papers and I understand the concept, it's still a difficult algorithm to control. You end up writing a whole bunch of code just to make it generate the terrain, and then you write twice as much code to get these edges under control. And without these edges under control, that's problematic for us. So what we're going to go for is something that possibly looks more like the Goddess terrain, except Goddess was generated using a full 3D set. So they're using an algorithm called marching cubes, and they're using a 3D voxel data set, somewhat like what Minecraft does, except that the marching cubes algorithm takes that voxel data and transforms it into something a little more palatable than what Minecraft has. So that's a bit complex for us, right? This is only a simple height map, and this will do better in height map form. We don't actually want the full 3D data going on here. That's overkill. So we're going to swap this out for something probably grid-based, and we're also probably going to end up swapping it out for something a little more controlled as well, because this right here, while nice, is not exactly what we're hunting for here. So, and actually, quick recap for anyone just joining, and I'm just going to show off kind of a minor detail of why this doesn't work, because I understand it, and I may as well pass that knowledge on to you guys, just to show kind of the current situation. The idea is that, pen, do you work? Yeah, you work. So it generates some random points on the plane, let's say this, and then it takes this, and say this, whoop, do you work buttons? No, you don't. I have an undo button here, though. That should work and isn't. Oh, it is. Okay, so the idea is that, say, this is our playing field, right? Nice square area, square-ish, square enough. Square enough, that's all we care. Okay, so what it does is first we do what's called a Delaunay triangulation, which takes these points and says, okay, there's a point here that we're going to connect to, and it generates triangles out of all your given points. So, for example, say we have another point here, it'll then add in a new triangle here. And it does a pretty darn good job. In fact, it does a fantastic job. Now, what it normally would do is, if you look at these points, those look nothing like our terrain. And that's because Delaunay triangulation isn't what we're using in our final form. It's actually using a standard Voronoi graph generating algorithm to create our vertices with. And so what it does is it picks 3 points in a triangle, and it says, okay, I'm going to generate a circle. Actually, let's change color here. Let's get some blue. So it takes 3 points that make up a triangle and says, let's find a circle that is made up of these 3 points. And it says, this is the center of that circle. Therefore, that is the center of this Voronoi cell that we're about to generate. It then picks, from these edges, points on the edge between the nearest vertices to it. So it says, okay, from here to here, here is our edge here, that is halfway between these 2 points. And also, you'll note there's this point out here, so we're gonna put a mark out here as well. And we're gonna mark halfway between each of these edges. And what this does for us is this is going to give us a triangulation So our first one's going to look like this, and that's not too special. But then we get between here, and we say, okay, halfway between these 2 points, there's going to be a new line here. And I'm sorry, guys, my lines are terrible right now. So halfway between these two are going to go off this way. Between these two, we're going to go this way. And we're going to go here. And you can kind of start to see how the terrain is going to get generated. Now, the problem is, some of these, it wants to generate a center for, and the center is going to be way out here. So it's going to generate a point that looks like it's out here, right? And so the problem is our center points aren't even in the main game area anymore. And that's because this circle that it's generating, so say we're taking the graph here, and we're going to find the center of it, it's going to take these 2 points here and this point here and generate a circle from that data. This one's actually really, really difficult to do as well. Let's see, where would that one be? Oof. You can kind of see the problem though, right? Here's our game area, and this is the area I want to generate terrain within, and yet it's generating terrain that goes out really, really far. Yes, I am using Delaunay triangulation for the initial triangles in the center, because Verneuil graphs are implicitly generated out of Delaunay triangulations. So essentially what you end up with are these giant polygons that go off into, you know, infinity way off here. And that's really difficult to control, right? You'd have to grab, if we were to do some error checking on this, we'd have to say, okay, we want to grab this one and cut it up here so that this is only one cell. And then this cell, we're going to use this edge, and we're going to have to cut it up here, here, and then attach it here. This cell, we'd have to attach here, here, and then go all the way up to here, and then over to here. And so it becomes a lot of extra work. Like I said, you end up writing about 3 times as much code, 2 to 3 times as much code, just for the generation as you do for the actual trimming. And then you have to do all the neighbor checks, and it's just monstrous. It's ugly. So, instead of fighting this system, we're going to go for something a little different. Let's get this out of here. And hopefully this new system will look just as good. That's the hope, right? Is we want to create something as interesting and diverse as this without doing kind of the norm or something boring. Like, I don't know, I consider Minecraft's terrain boring in the case of this game. Excuse me. And I have some questions. Is it easy to go from software development to game development? Yes, I'd say so. Once you understand basic software development, game development is a slight modification on that. For example, you know how to write basic code. Well, your game loop is essentially an infinite loop, right? Your program will enter an infinite loop, and that infinite loop will do little more than say, get input from the player, update everything 1 frame at a time, and then render everything. And then it'll go back to the top of the loop. Get more player input, update everything in the scene, render everything to the scene. Wash, rinse, repeat. Keep going until you have a game. So it's definitely not hard to go from software development to game development. At least in my opinion. Doop, doop, doop. Is it easy to go from game development to software development? I think that's even easier, because game development uses a lot of code and a lot of ideas that require high performance values out of your code. You tend to write code that is nice and fast, and then you also tend to learn a very diverse set of algorithms and data structures, which you can then apply to pretty much anything else. I mean, my last job was not as a game developer. My last job was just straight software development. I did optimizations for file systems. I did packet decrypting and a little bit of backwards engineering, or I guess I should call it reverse engineering on the Steam client. I did, what else did I do? I did crack open some games. I ended up also writing some code that dealt with DirectX systems and kind of writing overlays for any DirectX game. Being a game developer is helpful for some of that. At least for me, I tend to be a very generalistic programmer, so that makes it easy for me. Alright, so how do we rewrite this whole thing, right? Because the first big requirement for this code is that it must generate random terrain that fits within our range. So I'm going to go through and we are just going to rip out a ton of stuff. And I almost feel bad, but I don't. Terrain height, biome position, offset. So that stuff still looks good. Obviously, any code that still references the old Verneuil stuff, we're not going to want. Actually, the only thing that I may want to hang on to. So, not create Verneuil cell graph. That's going to be garbage. So let's throw that out. But generate cell points, nope, don't want it. Relax point, also commenting that says anything about it, no. And this is something you kind of have to learn to do in game development. You learn very quickly that sometimes you take a risk on something, and sometimes that risk just doesn't pan out. And so this is a case of, well, the risk didn't actually match. So we're throwing a lot of stuff out, but we've learned a lot of good lessons about how the ways that we can improve the game just through simple code structure. For example, I kind of want to keep this cell system. Now, I don't know what a cell means anymore. Cells used to be a single Verneuil cell, like what we had before. Cells now have to mean something somewhat different. We have to define an area in which this is going to be a biome cell. Right, we have to split the terrain into markers that will give us good, interesting edges for terrain. And that's something we have to figure out as we go, because I haven't planned this. Right, I just kind of decided I'm going to rip all this out, and that as nice as it is, maybe we don't want that right now. For example, I might want to actually keep the Delaunay triangulation code. I might. We'll see. For now, I'm just ripping things out, and then we'll put pieces of what we needed back in when the time is right.
Oh, goodness.
To make sure this all works.
Look where he dropped that from.
Oh my god. Dog, really?
He's wagging his tail.
Where'd the ball go?
I don't know.
My dog threw a ball at me, and I actually can't find it. It's around here somewhere.
Oh, it's right there.
Ready, set, dog, go. Alright, sorry guys. Getting distracted, because my dog is adorable. Alright, so first things first. And this is kind of the way I like to approach a lot of new game concepts and a lot of prototypes. If you ever make something, you just pick it apart into little steps and meet requirements as you go. And the big thing you want to do is make sure that you're meeting your requirements as you go. So step one is going to be obvious, right? We need terrain on the ground. We need something. Specifically, we need something that's just like flat and just meets the requirement of being inside our range. So, and we've got this entire big empty namespace now, so we've got a lot of space to work with. The question becomes, how does the code look before, and how do we want it to look after? Okay, so let's see. We're going to start with the obvious stuff that we already have, right? We already have a range. I don't know about cell count anymore. And I'm going to pull out this Verneuil comment because we're not using Verneuil again. But also, we're probably going to have to recraft a lot of this. For now, it should be fine. But honestly, we don't want to mess with things so heavily that, like, everything breaks. Also, let's turn off the people generation for now. Let's kind of trim ourselves back to basics so that we can put in the terrain, not worry about anything else, and then slap in everything we need for just the terrain alone, and then re-add the features back in one at a time, just to make sure nothing's buggy. Because if you change too much at once, you fall into the risk of having way too much changed, and it's difficult to pinpoint where the bug is coming from. That's why a lot of companies will say commit early and commit often. They want you to make a bunch of little changes so that the source repository always has a good idea of what you changed that broke things, if anything ever breaks. Doop, doop, doop. Okay. Cell graph, we've got a range. So step one, what format do we want this to look like? I still kind of like this cell setup, right? We've got vertices, we've got edges, and we've got a cell itself. And then we've actually got the graph that holds all the information. That's a good start.
Leave it, Apollo.
It's always a good start. Also, we'll have to refill in how A star works across this. Eventually. Find cells in area, yada yada. Without people, we don't have to worry about a lot of this code getting called, luckily. Alright. Step 1. Cut a hole in the box. Alright, so, let's just make some geometry and go from there. So, we have this cell graph. And we're going to jump into our terrain generation. We just have a create cell. So what I'm going to do, and I kind of like this idea, is splitting the cells into distinct squares for now. We're just going to call it a grid and just dump down a grid of cells. So we have create cell. We have probably some kind of position. Kind of a start point for us to work with. And then a range would be nice. And then we have to return something. So when we call create cell, we need something that essentially says, here is a new cell. And we either need to be able to call this a whole bunch and store the pointers away, or we need to be able to call this and pass it something like a list so that the information can be stored inside of that list. And let's look back at where we're calling all this from. So we have all the commented out code. Shadow spaces. So luckily most of this code is not dependent on the terrain. So we just create a world generator and we just say build terrain. And it doesn't really do anything other than take a world, a size, and the number of cells per square unit. And in fact, this number here will probably eventually get removed. Also, this build terrain might need a range as well. But that, I guess, that's all eventual possible things. So let's just let's just ignore it. Why not? Controllers, I don't care about controllers. We're not going to attach controllers to anything until we're well along our way. So, creating a cell, we could do two things. One, we could pass it the game world and just say, aha, we've got a game world, we're just going to throw all our stuff into the game world. I don't like that, because that gives us too much control. A terrain generator is not a world generator. It should only be generating the meshes and controllers necessary to build this. So I'm not going to have a full-blown... I'm not going to hand it the full-blown world. That's too much information. Now, it might not be a bad idea to hand it a node. Just a root node. For it to build off of. I like that a lot better. It keeps us controlled. Keeps us from kind of going wild with this. And writing all the right code in all the wrong places. Okay, so we've got a function. Now let's make us some terrain. So the world generation expects us to have already created a cell graph, and then it expects us to, let's see here. It expects us to have filled in that cell graph in such a way that we can not only get the colors, but then generate meshes and add them to a geometry list. That's pretty easy. I want it font metal, FNT mental. Oh, mental, not metal. Haha. And Pete Furious. Hello, guys. Glad you could join me as I tear out tons of code. How it goes. Sometimes you take a gamble and it doesn't quite pay off, which is kind of what happened for our terrain stuff. So, okay, most obvious thing we can do. We need a cell graph. Ooh, where does that cell graph happen? It's a new node. Okay, there's the terrain node. And here's the terrain cell graph. Okay, I see what they're doing here. And this is a cell graph pointer. So this is actually all we need to fill in. So we'd call terrain generation create a cell. And instead of handing it a root node, we're actually going to hand it the terrain cell graph. And then some points and a range. And the range is being calculated above, so we pass that. Game world, cell graph pointer. Yeah, I know. It's complaining about things that I knew. So you are a cell graph pointer. Now, let's think about this for a moment. So the first thing is when you pass in something like a pointer, there's a lot of things that can happen to a pointer. And it doesn't tell us, once again, I keep harping on this, but I keep doing it for a reason. For those of you who are programmers and watching, I want to make sure that you guys learn really good fundamentals here. And so one of the easy things to do is to just pass a pointer and have no idea what that pointer does, right? This is not a root node anymore. This is a cell graph. Right now, when you pass this pointer, you have no idea what this pointer is for, what it does, why we would ever use something like that. It doesn't give us any intentions. What we need to do is not just hand a pointer back, but we actually want to go so far as to hand a pointer to the pointer. So we're going to hand a double pointer back to this cell graph. And what this does is this signals to anyone using this code, myself included, because I'm obviously using my own code all the time. It signals to us that someone is going to be allocating memory and then releasing control of it, right? They're going to essentially allocate or deallocate to this, and then they expect you to clean this up later. And that is something that we really need to make sure we take care of. It's kind of what double pointers tell the world. Kinda, sorta. At least that's how I've seen it used a lot in the previous companies I have worked for. Because what we have to do at that point, we say, okay, we're going to take our cell graph, and this is going to be a new cell graph, right? We have already allocated to it, and we aren't going to be... we're not going to be deallocating that within the same function. Now, the one thing I just noticed is create cell is actually... I wouldn't expect create cell to create an entire cell graph. Just a cell, not the graph. So actually, this is overkill. Because we shouldn't be allocating this memory here. This should be getting allocated out here. That, or we should have a function that says create cell graph, which then calls create cell a whole bunch. Useful functions all to have. Void create cell graph, double pointer, cell graph. And this will take in a, range reference, but it's not actually going to care about positions. Does that seem right? That seems right. So the only other thing I'm worried about here is we don't know how many cells to create. For now, we're just creating one, though, so we'll expand this as we go. We'll make it work. Okay, so create cell graph, cell graph is a new cell graph. APH, there we go. And there aren't any constructors we care about. We can actually go so far as to do that, to call the default constructor. It's really a style choice there. Not something I care to dive into a ton, because it is purely opinion. Cell graph. And then we're going to pass in the range. In fact, you know what? Position and range are redundant data. They really are. I don't know why I never thought of this earlier. Sometimes your brain is on par and works, and other times not so much. Alright. And you'll notice that we can call create cell because it's in the same namespace as create cell graph, and we don't have to do the namespace declaration here. We could, but there's really no point. Alright, extra code for little to no reason. Why bother? Create cell does not take 3. You know what? You are correct, and that's fine, because we're changing this to create the cell graph. There we go. So this calls in, this calls new, and this is going to take our cell, and we're going to generate the right data and dump it in. So the cell graph needs a few things. We'll start with vertices. Vertices are the easiest thing for us to dump in right now. C4 point 2D, range min x, range, let's see here. So if we're going for the upper left corner, that's range min x, and range, let's see, do we want to do this in clockwise or counterclockwise order? Probably range dot range dot, thanks brain. Let's see here. I think we should be going in counterclockwise to make sure these get rendered correctly. Sherlock in HD, could I run the game in its current state? Nope. Just ripped out way too much code. It would be very unhappy with me. I tried to run it. If you give me a little bit though, I will definitely have this sucker up and running. So let's go in counterclockwise first, and if it doesn't work, we'll just swap it. So, we're going to start. Upper left is negative positive. Upper right is positive positive, and then you go positive negative, and then negative negative, right? Simple stuff. So, max max, and then we go max min, and then we go min min. And there's a smarter way to do this, but I don't really care to do cutesy things. I just want to get this running, and after we get it running, that's when we'll start to care about making this cleaner and better. Cell edge. Okay, so now we need to create edges out of our points. And actually, this vertex array uses garbage. I don't like it. Because our old vertex array required this index in here, and the index was kind of overkill. So let's just pull cell vertex out. Where's all our cell vertex code? Cell vertex. First off, this is way too much for something that we can cell vertex. Really? Nothing else uses it? No way. Cell vertex. Okay, here's the other thing that uses it. So you notice how this rewrite alone is giving us a lot more cleanliness in terms of where things go and where things come from. So we have a lot less types flying around, for one. Position, Anything else that's complaining? Yes, my unfinished code. That's fine. Okay, cell edge. Okay, so also edges have their own indices stored inside of them. That's way too much data for us to care about as well. So cell edges, you can bugger off. There we go. And that means, let's see, we need to update the cell edge class. So, I'm curious what you mean when you say how much it takes to program C++ on this level. Granted, I've been in the industry now, the programming industry, not the games industry, but I've been in a software engineering industry for the better part of about under 5 years, just under 5. But I could still probably program at this level a year or two ago, not with the same proficiency, obviously, but it's still worth it to give it a shot. Also, I just noticed v1 index, vertex 1 index. I just noticed that my initializers, v2 index, vertex 2 index, these initializers were done the, what I'm going to call the ugly way. Ooh, also, I wrote these backwards. v1 index, v2 index, cell 1 index, c1. Let's clean that up. While we're digging around, it doesn't take much extra effort for us to clean up a lot of the garbage that was floating around before. There we go. And you don't need to exist anymore. There we go. Much, much better. I like it more already. Multiple default constructors. No, sorry, that should go away too. Is that better? Yeah, we good? Cool. Okay, cell edges. So it needs vertices. 0 and 1. 0. And we're just going to do 4 edges. So between 0 and 1, 1 and 2, 2 and 3, 3 and 0. Well, Java's a good entry point, as is C#. Like, those are good gaming entry points right there. C++ is a little more in depth. Learning the memory management can be the trickiest part for a lot of people, but you'll find very quickly that once you start in on some very basic concepts, some of game development makes a lot of sense, and it's very logically indicative of its work. Sherlock, thank you for following. Hopefully you'll find this interesting and kind of informative. I'm trying to keep the whole broadcast be as... I guess the term I'm trying to use is just as educational as possible. Funny enough, one of the companies I applied to, and I'm talking with, possibly getting hired, is an educational games company. So that should be fun. I is less than... So I'm just going to clean up these lines below. Since we only have 4 edges, we can do this in a cute way, where we say add element, and you'll notice that all of our elements, 0 to 1, 1 to 2, 2 to 3, and 3 to 0, all of our elements are only 1 apart, right? So it's nice and easy. All we say is go between I and I plus 1. Now, that's almost correct, almost. You'll notice that works for 0 and 1, 1 and 2, 2 and 3, but 3 and 0 are going to give us some trouble. So instead of 3 and what would generate 4, what we're going to do is use our good old modulus friend and do modulus 4. So the moment you hit 4, it then says, I'm going to divide it by 4 and put the remainder in here. So it's going to do integer division and then put remainder. So it's like, what's 1 divided by 4? Okay, well 1 divided by 4 is 0, remainder 1. So that's going to be put in here when I is 0. So we still end up with 0 and 1, 1 and 2, 2 and 3. But when we get to 3, I is going to be 3. I plus 1 will be 4. Divided by 4 is 1 with a remainder of 0. So it's going to put that remainder in here. And just like that, in what could ostensibly be called 2 lines of code, we've added all our cell edges. Nice and easy. Alright, let's see here. So we've got our vertices, we've got our edges. Finally, cell graph. Come on. cell graph fingers. I need you to at least try to work with the rest of myself. Okay, so cell index is 0. Cell origin. So cell origin, range dot... Can I get the middle? No, I can't. Let's see. How can we find the origin? So the origin is always going to be the average of 2 endpoints. So we can say min plus range dot max. And if we put this in quotes, we're then going to multiply it by 0.5, which is 1/2. Same as dividing it by 2, but it's faster to do multiplication than to divide. Always a good rule of thumb. And then how many vertices? 4. How many edges? 4. The only thing left to do is to fill in this cell with the appropriate information. Cell C equals this, and then we're going to add C into our array. Really can't understand how so many game development streamers basically code 99% of the time. I understand it takes a long time, but how can you possibly code for hours and hours and not check into the game and to see if it even works? Yeah, I don't understand how they do that either. You'll find that once I create a system, I try and constantly run it whenever I can, and the easiest thing to do is when you make a system like that, once you have to make a large system that talks with other things, you end up putting breakpoints all throughout your work and just double checking it at kind of big waypoints to make sure that each waypoint, the data is as you expect it to be. And then you say, okay, it's working as expected. And you also will see them do a lot of debugging things, like in debug mode, I turn off the random number generator, or I don't turn it off, but I simulate a standard set of random numbers that I know are going to come up every single time. And I can sit here and like sketch it out on paper and say, my algorithm should do this. And then I go through and watch the code and say, okay, yes, it matches. Yes, it matches. Oop, something's wrong. Why? Where? What happened? And then sit there and figure it out from there. Because if you can logically sit here and think it out, then you most definitely can translate that into computer code somehow. So, let's see here. Cell edge indices. So we're going to start with the vertex indices. And we're just going to add 0. Actually, we could probably for loop this as well, just to make life easier. Equals 0. I is less than 4, plus I. C dot add, C dot vertex indices, add I. Because remember, we want indices here. And we're going to go also for our edge indices and add I. And that should be it. That should be all we need. Position is not a member. No, it's not. You are correct. Okay. Watch me have completely forgotten something. But I think we should be fine. Now that I've said that, something most definitely is going to break, but let's see here. Create cell graph, create cell. So you'll note, like, I just wrote a fairly small subsystem, but I'm still jumping in and making sure by dumping some kind of very, very key breakpoints in that I will understand what's going on. So let's see here. I run the test world. We generate a range that goes from -7.5 to 7.5. Now already, I'm not a fan of that. In fact, I'm going to stop right now and find game world. Your terrain size, I like even numbers, at least to start with. In fact, let's go with a small number. 2. Go between -1 and 1 on each side. I like that a lot better. Okay, cool. I'm caught up on chat. Every once in a while, I'm sorry if I stare off to the side and just kind of go quiet. I'm just reading as quickly as I can to catch up on all the things you guys are saying. Okay, so range -1 to 1. Like it. That's much better for me. So we're going to step in here. We create a new cell graph. Pointer looks fine. Data looks fine. So I'm going to kill that breakpoint. We're going to step into here. We've got 4 vertices. Everything here is so incredibly basic, I'm not really too worried about it. 3, 4, okay. And then the cell array. What I'm worried about now... Woo, hello, that's new. What array thinks it's getting deleted? And why is the data inside of it bad? Okay, so this cell... We're filling up its indices. Ah, okay. So I've had trouble with this before. So what I think I'm going to do, because I know what the problem is coming from. It's coming from attempting to move data around in unexpected ways. What we're going to do... The question is there a good way to simplify this? Also, we need to keep in mind, even though we're looking at code and we're just writing bare basic things right now, we want to also keep in mind that the information we store here might be something that we want to hang on to for serialization purposes, right? If a player says, I want to save my game, we have to keep in mind that integers, which is why you'll see I'm using vertex integers here, instead of pointers to, say, a point2D, you'll find that these integers and floating point number are all easier to serialize than something like a pointer, right? The moment that pointer comes out, things get bizarre, and it becomes very difficult to actually serialize things in one clean shot. Lots of talking. Needs lots of water. Okay, so problem number one. We're creating these cells, and these cells are full of integers. And I think it was the array of integers that was actually crashing. Interesting. So there's a pointer somewhere that it's trying to destruct, and that pointer is giving us a little bit of pain. Inside a cell destructor. That's bizarre. So the one thing I can keep in mind that I can really easily think of that might be causing us trouble is if you look at this, let's see, let's get that code out of here. If we look at our cell graph, we have an array of point2Ds, and then we have these weird arrays. This an array of cell edges, but it's of cell edge instances, and then we have an array of cell instances. I'm not honestly happy with that, because when you're passing instances around, you have to use a certain kind of constructor called a data move constructor, which sometimes can be a little messy, specifically in the realm of pulling data in and out of these. It's easier to move a pointer around than it is to move an instance around. At least not without using references all over the place. But you'll notice that a lot of my other code also uses pointers, so it might be better in this case to actually swap us over to use pointers. The problem is this is going to cause us to have to rewrite big chunks of code right now. Let's see. In Sherlock, I definitely do not mind right now. A lot of this is going to be, a lot of this rewrite you'll see is kind of mindless work, such as, okay, well, it's now a pointer, and a pointer means I have to do a dereference here, and a dereference here, and so on and so forth. Whoops. So I don't mind answering questions right now. In fact, I am more than happy to. How I learned to program like this. So I went to... Why are you complaining? From cell to cell pointer. Other call. Okay, this needs to be pointer too. Sorry. Distractions. So I went to 2 years of community college where I learned C pretty exclusively. After my 2 years spent there, I then went to a university where I spent another 3 years, pretty much, learning to program in everything from mostly C#, but I also learned a fair amount of Java, Well, I say a fair amount. I learned just enough to get by, honestly. I'm not a fan of Java myself. I learned a lot of C and C++ though, and that was kind of the big thing that got me off the ground. And, sorry, just removing things that are now unnecessary. And then the other big thing that I did to learn was I made a lot of stuff, right? I just made things that I thought were cool at the time. And that really, really helped. In fact, you'll find that a lot of my early projects directly correlate to some of the information that I happen to have stuck in my head now. For example, I learned a long time ago how to generate what's called a quad tree. And because I had that information, I was then able to better understand my professor when he said, I want you to build a 3D version of this, something called an octree. And I was able to use a lot of this information for a lot of my class projects. So I then took like a graphics class and said, I know you want us to make this thing, but can I make a game instead? And my professors were surprisingly cool with me making games and making I made projects that were much more difficult for myself, but because they were more difficult, they challenged me in new and different ways. So yeah, making stuff is really the big thing. What was the university course? I was at UC Santa Cruz, and I was working on a computer science and game design degree. Cannot convert from cell to cell. Yeah, that's fine. We just remove these. The game design degree allowed me to not just kind of learn how a bunch of stuff was made, but also it allowed me to go in and try my hand at making things I had never done before. For example, I had a class in graphics, and the class project was, with a team, we want you to go in and make something that is graphically intense, that requires straight OpenGL, and we want you to use a 3D camera. And so at that point I decided I had played enough Minecraft, I was going to make my own voxel terrain system. And with the help of 2 other classmates, we put together something very basic. It definitely was not like Minecraft level of anything, but for a first-time project, it was pretty intense and I'll put together. I've got a bunch of arrays somewhere. Get random point in cell. Where are you? Vertex array. That needs to be a dereference. So yeah, you'll find that a lot of project-based stuff is really the best way to go to learn how to make whatever you need to. And I used each of these as stepping stones. It wasn't just, oh, I've made this neat little thing, now I know how to make games. It was, okay, I'm going to try making a game. First I'm going to try making a platformer. Just make Mario. Something stupidly simple, right? Turns out Mario's really complex. Most of my classmates at that time could not put together basic collision detection code. Frightening as that was, because for me that was my junior year, I think. Kind of crazy, but we're down to 6 errors. We've got, okay, down to 2, cell edge to cell edge pointer. So we've got some array. And of course these aren't going to want to tell me. Cannot convert from cell to cell pointer. Oh, I bet. Oh, and they're in terrain generation. Somewhere in here. Ah, new. And you're a pointer. Arrow, arrow. So when I taught the class at UC Santa Cruz, what I ended up teaching was for students to begin with something easily within their grasp. For example, I had the first assignment, I think it was a text-based game, right? So we're not even doing graphics yet. Their first game in a game design course, no graphics, pure text. And I told them to make a game called Hunt the Wumpus. And it's actually a really interesting game. It's also easy enough that I think they were all first year students that had learned basic Java. And I said, A, learn C#, a new language you've never used before, and B, use this language to make a text-based game. And do it in 2.5 to 3 weeks. Ready, set, go. So that was fun. Maybe altogether a little more exciting than some of the students would have liked for their first week of class, but as I've been told many, many times before, there ain't no rest for us wicked. So, it's how it works. Alright, so this compiles. So let's give it a spin. Whoops. Of course, I turn on wireframes and then proceed to not run the game. Get vertex position. Generate mesh. Okay, so first thing, vertex indices. Okay, first things first. Our vertex indices is full of garbage. Why? Why are you full of garbage? So I'm going to dump a breakpoint here, and we're going to see just who is calling this and just where is it coming from. So we've already done our create cell graph, and if we want to double check, we can look at the cell graph out here and see, okay, here's our vertex array, here's the array pointer, and here's something cool I learned somewhat recently. If you, oh come on, really? Fine, I'll do this the pain in the butt way. Here's our cell graph, here's our vertex array, here's, okay, I'm going to take this array pointer and dump it into the watch. Now, that gives us a single pointer to a single value. And while that's kind of cute, what if we want to know about the other 3 values in here? Well, if you put comma and the number of values you want to see, it actually gives you the next value set as well, all the way down. So here's our -1, 1, 1, 1, 1, 1, -1, and -1, -1. So the vertices look fine, right? All the data that we inputted looks fantastic, in fact. If we want to just double check everything, we say, not that just the, what was that? That was the vertex. So let's go for the edge array and look at the innards of this. And you, hello. That doesn't look right. Let's nuke that and try again. I just want to make sure that all of these have the right data sets inside of them. Copy that expression, put that expression here, and then I want all 4 edges that I know exist. So you go from 0 to 1, you go from 1 to 2, 2 to 3, and 3 to 0. And you'll notice all of them have a cell index of 0 and -1, because 0 is our only cell, and because there's no neighbors, we're just using -1 as a non-existent array index to ensure that anyone who checks will kind of go, okay, is it greater than 0? No? Okay, there's clearly no neighbor here. Okay, so we called into generate mesh after we set up some other information, such as this biome color palette pointer. So we know what color to make it. This is going to be a forest type, and we have all the color specifiers here. That's good. So we know there's 4 vertices, which is fine. Top and sides. Okay, so because this is a square, right, and it's going to have its 4 sides. Ooh, I didn't think about this. Okay, let's turn off sides for now. Sides is overkill. In fact, let's leave the code here, but we're going to say there's 0 side vertices and see if that works just for disabling things now. There we go. Turn down the music ever so slightly. Okay, so we have all this code in here. We're going to turn off the side surfaces because we don't have any side data yet. We're not really at that point. It's too early in the code relationship to build that kind of data. Okay, let's try this again. Okay, we're still crashing, and that's fine. We have made a lot of big changes, and so this is something that we need to keep in mind when we do stuff like this. So our vertex indices, it's an integer, and that first integer is really friggin' huge. So this isn't right, and we need to figure out why and where this is going wrong. So vertex indices is a bunch of integers. And the question is, why is this going wrong? Where's vertex indices coming from? And why is it damaged? Let's see. Sorting the vertices, no. Cell. Where are you? Where's the code we use to actually generate all this? Oh, right, that's out in our terrain generator. So here's the edge indices. And here's the edge indices here. And that looks right. We're adding 1 through 4 to these indices. Okay, let's just follow this through the system. Alright, so we jump into our cell array. And we say, cool, we've got one cell, it's got 4 edges, 4 vertices, and it's got, here are the edges in order, and here are our 4 vertices. They clearly exist in both cell and in the rest of our system. And this cell array, this is valid. I mean, look at that. The data looks fine, right? If we look at the vertex, let's look at the cell data, just to make sure. Here is our only cell. It has a biome type of plains. Terrain node is null, which is fine. Okay, so we still have garbage data for one reason or another. This vertex indices is not getting filled in correctly, so we know something's wrong with our create cell graph function. Okay, it calls in here, and it calls into here. Vertex array, vertex indices. And then the cell array is made of cell pointers. And if we take those cell pointers back here, why is it garbage? Because the vertices look fine. Unable to read memory from here, of course. Something very basic is going wrong here, unfortunately. F11. Whoops. Didn't mean to do that. Too fast. Too fast for my own good. F11, F10, F10. Okay. That's a good pointer. That's perfectly fine. And if we look at who's calling this, we're passing in... Ooh. Could this be wrong? I'd hate to see if that was wrong. Let's... So I'm going to cover that in... Now granted, there's probably some order of operations that I should know that tells us the right thing in this case, but I'm not actually certain. So we've got our 4 points. So if we go cell graph, vertex array, and we look at the vertices, that is a good 2D vertex. Okay, so we step into the edge array, and we generate these edges, and we're handing the edge pointers back to this array of edge pointers, which looks fine. We then say, here's our cell, and the cell should have just a valid origin right now. Nothing else. And there's no indices there, and there's no indices here. So all of this data looks good. Vertex indices is an array of integers. Fair enough. And here's 0 getting added to the vertex indices, who just has an array pointer to dead data. So index vertices, 0. Looks fine. Looks fine to me. So now it has 0. And if I take this expression, put this here, and tell it to give me 4 values, you can see the garbage that's sitting in here, right? We've only set the first value, and therefore you can see the garbage in the other 3 values. And you'll see it fill in the garbage in each of these, which is fine. And then we take the cell array, which is made up of cell pointers, and we're just going to have it hand it the pointer to this data, which, if we look at this, all looks fine. But look at that. The moment we've passed this across, all this data gets invalidated immediately. It's like something is going wrong with the copy constructor inside of this function. You'd think an array of integers would be the easiest thing in the world, and yet. So okay, element count 0. We add a new element. We take the... What are we even inside? Okay, this is the adding a cell pointer. So this is a cell double pointer here that is at the array pointer. And then we pass in our element, which you can see all the data here. And this is a cell pointer being passed to a cell pointer. And if we look at these vertex indices, they're all garbage. Why are they all garbage? This is so incredibly bizarre. Also, you'll notice they're going to the same number. Part of me wonders, I wonder if I am doing this right. I wonder if I need a copy constructor in here. Or here we go. Here's something else I never thought of. The other thing we could do, just to make sure we're doing this right, is we could do this, and then we could say C equals, not new anymore, but we could say data C, and we're just going to call the constructor straight up. Cell double pointer can't be used. Oh, so you would be a double pointer. And then we say this would be equal to, oh man, we'd have to dereference this twice. That seems overkill. Let's look at cell real quick. I just want to make sure that it's not doing anything I don't expect. But no, there's a... But there is this default constructor. That might be messing with us. That really might be doing it. Just to make sure that I'm on the right track, even though that's the ugliest thing I've seen in a while, we're just going to double check. So, okay, we've created this new information. C double pointer. Man. Because we're creating the memory. We're setting the memory aside. That seems like I'm doubling up on all this information. That's the only reason I don't really like this a ton. Is that this seems like I'm going a little too far. It seems like I'm allocating the information twice. Let's watch the memory addresses, make sure this looks right. So, C is a pointer to a pointer, and it exists at a valid memory address, and the memory address that it points to, you can see it's been freshly created. That 7F with a bunch of C's tells us that we've created this. And this is something that's only done by this engine, so I wouldn't say it's something you can take with you to any other location that you use programming in. And then you can see we call that 3, 4, F9, F9. So the question is, does this data still look right when we back out of here? So we've got our cell graph with all of its vertices, and if we look at the cell array and its vertex indices, okay, it now holds good data. It now is holding perfectly good data. Why? So the reason why, we tell it to add an element, and it gives us a pointer to a pointer back and says you can allocate something to this, and then we then fill in that information. Okay, it makes sense. I'm not the biggest fan, but I think I understand why. Because the other way to do this, if we wanted to, we could say this is a cell pointer, C, and we could do all the normal information here. And what we would end up doing is we say add element, and then we say this is the cell. I don't know how I did that incorrectly. There we go. And this should be cell and cell. There we go. Right? This works just as well. Do you want to stop debugging? Yeah, sure, why not? Let's see. Is this C++? Yes. Base 0, this is. Which Danny Fritz already beat me to. Well, fine. Be that way. Why do you need a pointer to a pointer? So, the reason I need a pointer to a pointer is because if you look at how this cell array, or how any array in this engine runs, let's see here. Can I find the actual definition for an array? Here it is. So when you give it a type inside of an array, you then store away a type pointer, because you want this to be a dynamic array of whatever type you hand it. In this case, I've told it, where is it? In this case, I've told it that I want this to be an array of cell pointers. So what the template is doing is it's saying, okay, this is a cell pointer pointer, so that it is actually a one-dimensional array. It's not actually a two-dimensional array, but what it's doing is it's storing things in kind of the pointer context of what we're going for. So the question is doing this with cells and pointers overkill? Or is doing this with cell pointers overkill? Because it's already storing the information in pointer form. Is that overkill? I think it is. I honestly think it is. But it seems really bizarre that it would be overkill. I'm still really getting used to his data structures. And when I say his, I mean the engine author. It's something that just requires a lot of getting used to, unfortunately. Let's see here. The only other thing is that by doing this with pointers of pointers of pointers of pointers, where is it? Is point in cell, point generate mesh. Oh, right, we're doing this out in terrain generation. The only other reason why this isn't so great is that, let's see, if we call new, oh, also, music, don't stop. Please don't stop. The only other reason why I don't really like this is it seems like I am doubling up on way too much data. And I'm just going to look at the array type real quick, just to make sure I like what's going on here. So it has a standard type pointer, just a standard operator that lets you dereference the array and say, oh yeah, this is a pointer to the array. You can also say begin and end. I like those. And then if you hand it a type reference, we can check if it contains an element. So that tells us some idea of how this is expected to be used. It tells us that we're not actually expected to use a pointer in this case. And just to kind of double check how the engine uses it, you can see here's an array of event types, or here's an array of point 3Ds that turns into a point 3D, a point 3D pointer, or a vector 3D pointer. And you can see that the way the engine uses this is not... It's quite unlike the way we are attempting to use it. Although there are some cases where he uses material object pointers, right? So that's not a terrible thing. Get array. And I guess the only other thing to think about is this immutable array I'm hunting for, where it actually defines the bracket operator. Let's see here. Can I actually find class array? Yes, of course. And it is of, oh gosh, okay, so this is templated. That's why this is difficult at times. Set reserved count, set element count, add element, insert element. So what I'm hunting for is its operator override. Did I write cell.h? Yes. Yes, I did. Well, I wrote some of it. Some of it is my partner who is helping me out somewhat. He's unfortunately been insanely busy lately, so he actually hasn't done any work on the project in about a month, but that's fine. It's all good. So I'm still not able to find the operator that does the brackets, the bracket operator override. Operator. Okay, an array object can be implicitly converted to a pointer to its first element. This allows the use of bracket operator to access individual elements of the array. Okay. So now I understand what I'm supposed to be doing with this, and cell pointers is definitely overkill. So this is an array of cells. That is fair. Let's think a little bit here. Now that I've swapped that back, a whole bunch of stuff is going to complain in great new ways that I was not handling well before, which is fine. So stuff like this is fine, but what we want to do, let's see here, cell pointer cell equals cell array I. Well, no. What we want to say is equals the dereference of cell array plus I, which doesn't look like it's working. That looks like it works though. So then we just say cell arrow. Yeah, there. Okay, I have learned something stupidly invaluable today about how this engine works. Okay, this is much, much better. I love it. Especially since you can seamlessly swap between array and pointer to. So much better. Specifically, let's see here. For int, this is this plus this. Ooh, yeah. Cannot convert from cell to cell array. That's fine. We can just do that. Granted, we need to do a check if other cell index is less than 0, right? Remember, we have those neighbors. Yeah, so the one thing to keep in mind is that C++, I'm answering Merg Gaming's question here, so you can use the array from C4 Engine like an array in, for example, JavaScript, so you can insert elements and remove them. Yes. So the idea here is that C++ does not implicitly contain a dynamic array class. That is why he has created for the engine a C++ array object that allows me to have dynamic arrays. So I don't have to do that work. And that's a good move for an engine to do. Base0 asks any reason why I'm not using STL. The engine already overrides everything in terms of memory allocation because it has a memory manager attached to it. So it overrides new and delete. And by doing so, that first off breaks the way STL likes for things to work. So STL is kind of out the window right there. The other reason why I'm not using STL is because STL is kind of garbage, performance-wise, right? It's a messy thing that I really don't like to use when I can help it. Unless I'm working on site, I don't really care about performance. Its implementation is just kind of mucky. It's designed by committee, and that never ends well. So the reason why I'm using non-STL stuff, one, the engine doesn't really allow it, and secondly, he's written game-specific classes, such as this array class, that allow you to do things much cleaner and much more performantly. Is that a word? Performantly? Performantly. Yeah. In a performant way. It's an adverb. Cool. Learning all kinds of good stuff today. All kinds of good stuff. Which is how it should be for any programmer. You should never be able to go in and say, well, I did all this work, but I didn't really learn anything today. Like, that's not right. It really isn't. Cell pointer cell equals cell array plus I. Then we say cell, and then, oh, actually, yeah, why not? Let's use references. References are better. References break less often. Cell array I. Cell dot. Cell dot. There we go. Much better. Excuse me. Let's see here. Cell array. Yep. Dot. Dot. Cool. We're just going through and replacing all the cases. We're actually swapping some of our code back to how it was before. Not the end of the world. I wonder why I'm using... Let's just swap this back to a standard cell. Because all the data we're pulling out of it, if we dereference it once early, that means we don't have to dereference it with all these arrows every time we want to access data that's inside this object. It's a lot faster and a lot cleaner. What's the advantage over standard vector? I thought standard vector is pretty much as good as it gets. So standard vector is pretty much as good as it gets. That is one of the few cases where STL's work is pretty close to what the standard is. The only thing that standard vector does that this engine does better is that when the engine starts, it sets aside a giant block of memory. Like, we're talking in the... Well, I think at this point he sets aside somewhere in, like... I actually don't know. It's probably something like a quarter gig. Maybe set aside 250 megs of memory. And then whenever you call new, it takes a block of memory out of that giant chunk and hands it to you. And then when you call delete, it just puts it back. Whereas STL vector, or standard vector, I guess I should say, whenever it calls new, it's actually allocating off of the heap, which takes more time than it does to simply take a pointer and return it. So that's the one big thing that this engine and this array class specifically has over an STL vector class. Let's keep going here. Let's keep this sucker moving. And I'm sorry guys for all the basic little refactoring things going on today. We're rewriting so much code and we're looking at the basics of why so much of this code exists that we're spending a lot of time on kind of nitty-gritty things that we might not have cared about before, but that we're going to take a second look at again and just make sure we're doing everything correctly. Cell graph, cell array I. I wonder why we're not using the cell here. Cell dot that. This is a cell dot. Okay. We're almost done setting this, honestly, back to where it was, because I did not fully understand things, and now that I do, I'm seeing how many of my changes were in error. Oh. Once again, this could just be cell dot. It also looks like I'm getting a good chance to clean up bits of code here and there, which is nice. And finally, you give me a pointer when you do this, and we just do that. Let's see here. We take the pointer, we assign the data back into it. We're just going to copy... Okay. That should not be a reference. That should be a dereference. Add element. Let's think here. Let's think for a moment. This So I kind of like having the cell pointer that it allocates for us, and then we fill it in. So let's do it this way. Even though it kind of breaks the flow a little bit, it does allow us a little bit better control. And let's just double check that this works before we send it off on its weary way. Whoop. Why are you having so much trouble with just an array? This is so bizarre. I've never... Well, no, I ran into this before, I think. We're calling just a basic constructor because it's giving us a pointer. Let's see. What does this pointer look like? Is this a valid pointer? Yeah, it is. It's just a basic valid pointer. And so all we should be doing Oh, and it's already called the constructor once. Oh. It's already called the constructor once. Calling the constructor again is likely confusing a lot of the data that's on the inside of this class. I wish I could... That's really interesting. Alright, let's see. Let's think of how we want to do this, because it's cute that they already call the constructor for us, but I really don't like it either. It looks like add element, the one without anything in it. You can see here it calls new and type, and it just, that's it. Default constructor, throw the data pointer in, it's done. Versus this calls new and then passes in an element by what essentially is known as an R-hand reference or a right-hand reference. But when I do that, if I generate an instance, the instance then immediately gets destructed at the end, and part of that destruction involves an array that's never been used. And if you call new on this, or not new, if you just call the base array constructor, what happens? Here's our base array constructor. No, that's not it. This? One of these. One of these suckers in here. Constant, okay, explicit. Array count equals 0. So the one that has an integer count. This is the one that's getting called. Let's double check this. Actually, let's sell I'm just trying to surmise what happens when you call add element and hand it an instance like this, and then it takes that instance and attempts to move the data from one place to another. I'm wondering why the array inside the object is getting kind of manhandled in such a way that its destructor suddenly becomes unhappy. I'm just going to range min, range max, times 0.5, and 4 and 4. What is going on here? Oh, I wonder if it's these 4s. If it's expecting data, and then that data is never happening. Okay, let's take this for a moment. Turn this off. And just walk through this and see why this might be breaking down. So we handed it an instance, right? Here's the constructor of the first instance getting generated. And you can see that the data is going into it well enough. And we're creating these arrays and telling the array to call new. Note, so if the count is greater than 0, which it definitely is, then we call new on all of this data. And here you can see inside the memory manager it's doing some allocation stuff. I'm actually going to step out of that because we really don't care about something like that. I expect that to work 100% of the time, right? So that, whatever, don't care. Okay, so we have a valid array pointer to a bunch of what are pointers, right? There are 4 pointers of size whatever. Well, it's a pointer, so it's a 32-bit object. And we've got all this array data in here. And then it immediately is destructing that array. Why is this getting destructed? Okay, first off, this is terrible. Vertex, it's creating an instance of an array and handing it to that. That's not good. We need to, let's see here, under elevation, vertex indices should be, yeah, constructing using a standard count, num vertices. That's not good. And once again, see, this is code before that was causing me trouble. And because I'm doing a big mass cleanup all at once, this is allowing me to clean up a lot of stuff I didn't really want to deal with before. The code worked, and I just didn't question it. And origin, cell origin, oh my gosh. Origin, yeah. Cell origin. Okay. Whew. So the difference here is that before I had an instance and I was calling another instance and then setting the two to be the same. Copy constructors all over the place. Now, with everything living inside of this initialization section, this allows us to initialize things using a standard constructor instead of using a copy constructor. It saves us a lot of time, hopefully. That's the hope, right? We write this code and expect it to do what we tell it to, whether or not it actually does that. So you'll notice this time, okay, here's that array, right? And we say, okay, it's got a count of 4, so we set that pointer, and you'll notice that there's no destructor getting called after each of those. Before, there was a destructor happening, and that's really friggin' messy. And then we add the element to the array. Good. And when we step out of this, nothing crashes. Okay. We got it, guys. Okay. Yeah. Me likey. Okay, so first obvious thing here. I don't want to hand it cell C equals this C dot C dot. And then we are going to try handing it the cell instance. What do you mean? Invalid key combination. Control, what is it? Control Shift B. It's always the same thing. Sheesh. In before it doesn't work at all. Yeah, watch. So that's not... Danny, the one thing to keep in mind, and I'll show you this real quick, those aren't all parent classes. It's an initialization structure, so the first obvious thing you can do with a cell is you can say, yeah, any parent classes, you can say, oh, it inherits from this public class. But the other thing you can do is you can initialize variables that are members of this class, which is what all of these are, and you can do that inside of this initialization section as well. I find it a lot cleaner to do things in here because it's telling you that we're not doing work. It's the same as doing int index, cell index, right? It's the same exact thing, or not. It's the same as doing that, which in the case of an integer is the same as this. It's nifty. It's a nice thing to know, yes. It's not that these are all... I'm not the craziest person in the world. These are not all base classes. They're just member variables. You'll see that I put base classes over here on the right-hand side, and that I'll put all my variables underneath, if I can. Where was I? Okay, so we add the element, yada, 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 yada. And when I hit F9, good. Everything destructs fine. Whew. And just to double check and make sure that all our data looks good, what's funny is all of this wraps around eventually. We look at our edge indices, and look at that. See? There's our 0. That's what happens when we program things and do things the expected way. It took a bit of research, but we figured out what the heck was going on. So, the hope now is that it is going to generate terrain. Of course, it crashes. Oh, because... because Rob isn't thinking too clearly and forgot to turn off code that we aren't using quite yet. So we're not going to use the visibility code right now. I just turned off all the visibility stuff in hopes that... Hey, look at that! Right? Simplest thing ever. It's just a simple quad. And this represents a cell. Simple, easy peasy. But already the code behind this single cell is a lot cleaner than the old stuff used to be. And that's part of why I'm doing this rewrite. There was just too much stuff going on that wasn't allowing me a user level control of this data. Now already I have control over what I'm calling a cell now, which is going to turn into a grid of like-minded cells. And we're going to take that and break it out even further very quickly and easily. For example, we'll have const float. Let's see here. So we need to break the cell graph into multiple graphs. Or not multiple graphs, but the one graph into multiple cells that share edges. And this is where things get a little difficult, but it's not the end of the world. We'll want some kind of resolution. Specifically, the same way your monitor has the number of pixels per screen, we're going to want a certain number of cells per graph. So you give it a range, and then we're going to take that range and break it up into all its pieces. So Chalkman, the new vision for the terrain is something more along the lines of... I'm trying to think of a game that's done this before. I know Goddess has, right? I'll pull up a... Let's see here. Goddess terrain. Because this stuff's pretty. And this is what I ultimately would like this to look like, with more flat space that allows us to more easily create settlements that have more walkable space and more buildable space as well. For example, let's see, where's a really, really good one? I have a few favorites in here. So this is one favorite, which, of course, come on. Okay, fine, fine. You're not going to give me what I want. Alright, here. I like this. This one looks good. Can I view an image? That's... No. You are a tiny image. Well, I say tiny, but it's not. It's not all that large. Oh, man. I really wish some of these were larger images. But they seem to all be... Why are you all tiny little images? Okay. View image. So, I like this terrain, right? If you look at this, it's got lots of layers. Do a lot of programmers touch their noses a lot? Yeah, maybe. I don't know. That's just kind of a habit. But I like this terrain that breaks... Now you've got me all, like, thinking about it. Now I've got to really try not to. But if you look at this terrain, it's very height map oriented. Granted, it's not being rendered in a height map. It's being rendered, I think all of Goddess uses what's called a marching cubes algorithm, and actually uses 3D voxel data, but that's not really what I care about. The thing I care about here is the fact that you have lots of flat space, and using something like a building tool will be very obvious. You can almost break the world into a grid and say, on this part of the grid, I'd like to build this, and so you can plop it down and it will work. Do you have a plan to have one plane of the same height as one single cell? So that would require me to build some kind of nested cell system, and I'm not sure that's quite what I want. I'm still thinking that I'm going to do something that is... this is kind of where I'm still thinking about this. I just wanted to get the root code in place to build out something like this. Get those voxel terrains, or not voxel, the Verneuil graphs out, just so that I could figure out a good way to get this started. So I don't really have a big plan yet. The big hope is that I will be able to build something and then use or edit it after it's been generated. For example, before the old Verneuil stuff, it all worked off of random points put onto a plane, and that didn't give me enough control so that I couldn't carve out a space and say, this space is for a settlement. This is where I'm going to put my starter buildings. Before, it was so difficult to get to that endpoint that you honestly had to find some really bizarre intro points to get into and then modify all that data. Also, they didn't play well with hard boundary edges, as I was kind of explaining when the stream first started. I need to reticulate splines. Eventually maybe, but not now. Not yet. First things first, we got to put something in place before we can have anything useful going on here. And the big hope is that I can do something height map based, right? So we can do height map terrain, right? You've seen probably a lot of stuff like this before. It'll start... that's actually not really what I want at all. I actually saw a really good example of it earlier, and now I can't really find a new one. So something like this would be a good height map based world, right? You've got slight changes, and then you've got the big changes. That's kind of nice. I'm missing a reference you guys have going on there. I don't get it. Whatever. So yeah, this is kind of something similar to what might be a nice end product. because the edges here, you can very clearly tell where you can and can't go up and down cliffs. And the other thing is that you can still see there's a good gradient for the way in which terrain can be generated that is randomized enough that you can have stuff like, okay, here's a nice little valley, and then you've got these high cliffs surrounding it. And that would give you, as a survival sense, you want to say, okay, do I want to be up here? Or do I want to be down here when I create my initial settlement? Or maybe I'd like to be way the heck out here, right? It gives you some initial thought of, well, where do I want to start my settlement? Because that's the first choice the player is going to end up making, is pick a spot on this map of where you might like to start, if that becomes a first choice. I kind of like that as a first choice, though. And we're going to keep using the Perlin noise, if only just to, or not Perlin, sorry, the simplex noise, if only just to have a gradiated kind of terrain. Like something like this. This is great. You have your terrain, you have all the little valleys through which water can be running. And then something like this forces players to think kind of, okay, do I want to try building a bridge? Do I want to try sending someone through the water? Stuff like that. That's why I really, really like the idea of height-mapped terrain. You can very clearly see from a top down what is where. And this is actually a really good example of something I would love to have my terrain generator come up with. Just basic height map data right here. Looks good. I like it. We'll see. We'll see if we can get to that point. So we've got resolution, and we want to say, I don't know, 1, 2, So the question becomes, how do we want to generate grids into our graph? And then how much data do we want to sit inside a given grid? Why don't you just use a grid-based terrain and load an externally generated height map? Because I'm using procedural terrain generation, loading in like bitmap kind of height maps that have been generated elsewhere, while nice, is going to be a little more in-depth and difficult than it is to just generate everything in engine, like I'm currently doing. The SimCity loading screen claims to reticulate. Oh, okay. I like SimCity. That was a good one. Although, interesting. We'll see. One thing at a time. One of those things is going to be ditching my sweater because it's really warm in this house. Despite the rain outside. That's the funny thing. Well, actually, no. The rain's keeping it nice and warm. We've got all this lovely cloud cover, and California is getting rain that it definitely needs. So, let's say we're gonna want 10 units. Let's even make this an integer for now. Maybe we'll break it up into a float later. But we want 10, and this will be units per square unit. Or I guess I should call this cells per square unit. Per square unit? So 10 cells per 1 square unit. I don't really like that measurement system. Maybe we'll say cells per linear unit, just so 1 unit long will have 10 cells across, and then a square unit will then have 100 cells. Let's see here. And so this is going to require us to take that range and make it fit the needs of the resolution, but that's not the end of the world either. In fact, let's think here. So we need to come up with a new range, and then we need to pump out ranges and hand it to this create cell function. Let's see, it will be... We'll actually want to do y first. Y is less than range dot max dot x minus range dot min dot x. And we're just going to make an int out of this and do a little bit of floor to inting, flooring. To get this to work, we'll say our x length x cell length is going to end up being C4 floor to, oh wait, no, that's a game util, isn't it? Really? Do I not have, oh, I don't have. Also, why is simplex noise down with the engine stuff? Let's get that out of there too. Okay, there's our floor to int. So we take the distance between these, and we multiply it by the resolution. And then we do that into our floor to int function. And we just want to do the same thing for our y cell. Y and y. Actually, what's funny is, oh, but the floor to int is going to force us to put this into a two separate variables anyway. Okay, never mind. Okay, so y cell length. Oh, and we need to get the range put in here as part of our system. We can't just say, oh, well, you know, it starts at 0. It actually should start... Ooh. We need to kind of force all of these into integer form, is kind of what my brain is telling me. Or I kind of like this better. You should be a range of integer 2Ds. Haha, sucker. I like that better. That's much better. Let's change our functionality to match this. Cell graph, range min x, range max, yes. All of this still looks good, except for the fact that it doesn't look like you can add integer 2Ds together. At least not in the way that I was doing it. Integer 2D, range, I guess I'll call this, oh, this is the origin I'm trying to compute. Ooh. Okay, I got it. We're still good. We got this. Point 2D, range min x plus range max x. We need to put this in some parentheses so order of operations doesn't bite us in the hind end. Range, whoop, range min y plus range max y times 0.5f. Sorry about that, guys. I still need to, remember that noise gate I said I needed to set up? Yeah, I haven't done that yet. Dog. Don't. Okay. I'm playing with my mute button a lot just to try and keep him from maxing out stuff. Alright, looks like he's quieted down. I can unmute myself just so he doesn't blow anything up. Okay, so we've got our point 2D. We're going to call this origin. Really? The moment I unmute is the moment he decides to go back in? Oh, dog. Okay. Okay, so that origin looks nice. And since we have everything now in integer form, we can actually do, let's think here. For, float y? Oh gosh, but now I have everything being done in integers. So okay, this still needs to be a point 2D. I can't quite eliminate the point 2D and use integers all over the place, as much as I would like to. So let's at least put all this code back to a cleaner state. There we go. And we need to swap this back. You take point 2Ds, not integers. Does this really simplify our life? Yes, this still simplifies our life enough that I care. So